All right, folks, welcome back. We're going to do a couple of indefinite integrals here today and see how far we can get with this. All right, so here we have 2 over x squared minus 9, and so this is terrible. Okay, plus this. Okay, that might be better. So 2 over x squared minus 9, and then x squared minus 25 over an x. Okay, so here we go. So let's go ahead and deal with part A here. So what we have, 10, right, is 2 over x squared minus 9. By the way, I just write these, I mean, I don't craft these specifically because this is a pretty typical kind of an integral. So, you know, I'm not going to, well, I will apologize for the numbers because, you know, like I said, these are pretty much made at random for me. So there's not much effort that goes into making sure that they're nice numbers that happen here. Okay, some problems I do, but a lot of problems like this, like now we can just do it. Okay, so hey, this is a partial fractions problem. Okay, now if your first thought was to say, well, let u equals x squared minus 9, and then my du is equal to 2x, there's no x up here, so you can't finagle this to do anything. Okay, so we're going to have to use partial fractions. Okay, now one thing I will do is try to make it so that this partial fractions problem isn't insane as far as like, here's 4 equations and 4 unknowns you got to solve. Like, we're in the middle of a final exam. You are not, you know, I don't have time to do this to you, and you don't have time to solve it. So we're not going to worry about the hardest ones, okay? I just want you to be able to, right, be able to recognize this and go ahead and solve it. We're not trying to prove anything here. Okay, so let's go ahead and hit this. So this is going to be, right, a times x plus 3 plus b x minus 3 is equal to 2. So equating my coefficients, right, here's my x values. So we have, there's an a plus a b. Any x values on the right hand side? No, so there's none of them. And then here's my constants. Okay, so we have 3a minus 3b is equal to constant 2. Okay, and then we just got to solve this. And there are about, you know, seven ways to solve this, one for each day of the week, maybe 2 on Sunday. Okay, so I'm going to multiply this one by 3. So we're just going to get 3a plus 3b is equal to 0. We have 3a minus 3b is equal to 2. I just took the second equation and just moved it over. Add these, we get 6a is equal to 2. A is equal to 2/6, which is a third. By the first equation, b is, right, b is equal to negative a third. So I don't expect you guys to fight this. If you end up with, like, there's a whole bunch of this stuff, check, because sometimes I will engineer this thing so that maybe you'll get like 4 equations, 4 unknowns, but it'll really be 2 systems of 2 equations, 2 unknowns. Okay, so don't, you know, if you're looking at it like there's a mess, there's probably a fairly quick trick to see if you can make it a smaller problem, or there might be an A, B, and C, an A, B, and a C, and then maybe the last one is just C. So you just solve that one, plug it back into this, and you're back to 2 equations, 2 unknowns. So the point I'm trying to make is, while I don't necessarily engineer these to be perfect, I will not go out of my way to engineer them to be insane. Okay, so I know what the structures are to make them worse, and I'm not going to do that to you. Okay. All right, so here's our substitution, right? So we're just going to integrate. We have 1/3. That was my a, right? A was a third. And what did I set a up as? X minus 3. So this is 1 over x minus 3. Okay, and then b was a minus 1/3, and that was 1 over x plus 3. Technically, I guess you could put the 1/3 up here. That always kind of threw me off when I was trying to integrate them, so I just moved them off to the side because integrating a constant times a function was, you know, that always struck me as more straightforward than trying to put the 1/3 up here. That was me. Okay, so integrating this, right? This is just a logarithm one. So this is going to be 1/3 ln x minus 3 minus 1/3 ln x plus 3. Don't forget the absolute values. I don't know what x is going to be. Okay, and then our constant. Don't forget your constant of integration when you do this. Okay, it's automatic -1. So you got like, hey, I got a perfect square. Like, no, you forgot your c's. It's -1. Turns your a into a b. So I'm going to go ahead and factor out the 1/3. And we have ln x minus 3 minus ln x plus 3 plus c. And then just to show you guys that you can do this, I know some of you forgot. Right, we could take our x minus 3 over x plus 3. There's our c. Okay. Right, logarithms turn division into subtraction. So you can turn subtraction back into division by combining them into one log. Okay. All right. Number B, or part B here. Oops. Forgot it's over here. Okay. This one looks a little harder, right? It's integral x squared minus 25, the square root of x squared minus 25 divided by x. And let's see what we can do with that. Okay. So this is the square root of x squared minus 25. Oops, not that big of a square root. It's a tiny square root. All right, there we go. Over x, we're integrating, and we have a dx here, right? So we're good. Okay. Again, if you try to do a u substitution, like, wait, I have an x, like your d is going to be at the denominator. Anytime you end up with like a 1 over a du, you have made a tragic mistake. Don't do that. You end up with this, you've made a tragic mistake. Don't do that. There's a spot in differential equations where you do end up like this, but this is a very special form, so I'm not going to say like never, ever, ever do this, because it does happen. There is a technique where we use this, but for this class, we didn't get into this. So if you end up in this position, don't use this. Okay, all of these for our class are very bad positions to be in. Okay, this is like when your opponent announces like, okay, I've got checkmate in 4. Like you put yourself in that position. Okay, don't do that. If you see this, like, I got to pick a different technique or a different u or something. Something's got to change. So going on to my next one, like, I could try integration by parts. I don't really want to do that because I know that this derivative is going to never end. 1 over x as a derivative is never going to end. So I can do that, but I don't think it's going to get me anywhere. And then I remember, I'm like, oh yeah, there's the triangle stuff when I've got a square root. Let's build a triangle. Okay. So anytime you have like a squared plus b squared equals c squared kind of a situation, this is what you're really looking for. Okay. So if I'm looking at my triangle, right, I remember my Pythagorean theorem, what kind of a format do I have? Do I have this one? Or do I have like an a squared, I use b squared, whatever, but is equal to c squared minus b squared? Like, I think we have a match. I think we're looking at something like this. So what's my c squared? My c squared is x. Okay. I'm going to change it to an a here. And then at this point here, this is going to be x squared minus 25. Okay. I really should have changed this to an a because I like my adjacent side to be a. This is where I am with it. Okay, so yeah, here we are, triangle. So what we're going to do is we're going to say we want just an x, because every time you make a substitution in calculus, you're going to have to find the derivative of that substitution. And I don't want to find the derivative of this function here. That looks kind of scary. So what we're going to do is we're going to say secant, although secant looks scary too. Secant is equal to x over 5. So x is equal to 5 times secant theta. Okay. So don't be worried about it. You know, again, there are problems like this where it's really difficult, and then there's problems where they're pretty straightforward. Okay. We're on a final exam. You're not looking at really difficult and tricky problems. You do have to know, though, right, derivative of secant, secant tangent, okay? Knowing the derivative of cosecant would probably be nice too, but the way you set this up is that you always try to get either a sine, because derivative is a sine of cosine, or secant, because the derivative is positive. So if you do cosecant, right, derivative of cosecant is going to be like negative cosecant cotangent, and we just don't want to deal with the signs. SIG and signs, not SINEs. Okay, and now we're going to go back and we're going to substitute. I have everything I really need here. Okay, so here's what we're going to do. We're going to say, well, x was equal to 5 secant theta. So we have a square root of 5 secant theta squared minus 25 all over. Right? And what's x? X is 5 secant theta. Okay, that's my x. And then my dx is 5 secant theta tangent theta d theta. Okay, you need all those substitutions. All right. Now, you could have made this slightly easier, okay, by, that's pretty tame, realizing that the square root of x squared minus 25 divided by x is a sine of theta. Okay, so alternatively, you could have said this is the integral of sine theta d theta, which is going to be 5 secant theta tangent theta d theta, and worked it this way. We're going to end up in the same place, so it doesn't really matter. Okay, I'll show you what's going to happen there. But this is the way your book explains to you how to do it. And again, I'm a big proponent. Draw the damn triangle and set it up and solve it. I would not memorize like, well, if the top has a radical and the position of the hypotenuse is first, then the substitution you're going to make, like, don't, you got enough to memorize, okay? I can barely keep derivative of secant and derivative of cosecant straight. I'm not messing with like trying to come up with which conditions you substitute. Just draw the triangle. It solves itself after that. So, integral, we have 25 secant squared theta minus 25 square root divided by 5 secant theta times 5 secant theta tangent theta d theta. And you might notice that a couple of things tend to cancel here. We have a 5 secant theta, we have a 5 secant theta. Okay, and then we're going to need something from the identities section. Okay, so we'll come back, we'll put this aside and come back to it as soon as we get to the same spot. All right, so remember that sine squared theta plus cosine squared theta is equal to 1. And I never remember the other two, but I've got a secant I've got to deal with. So let's divide by cosine. Okay, that's a cosine, not a secant. Okay, so that is the tangent squared theta plus 1 is equal to secant squared theta. So tangent squared theta is equal to secant squared theta minus 1. That'll come in handy in both cases here. So we got 25, so let's go ahead and move that out. Remember, this 5 got canceled. All right, we have integral, that secant got canceled. So we have secant squared theta minus 1. Where have I seen that before? Secant squared theta minus 1, that's tangent squared. So we have tangent squared theta, square root, times tangent squared, tangent theta rather. D theta, don't forget my 5. Derivative of tangent, or derivative of, not derivative, square root of tangent squared, we're going to call that tangent. Tangent. Okay, d theta integral 5. So we're going to have 5 times tangent squared theta d theta. I still have to integrate this. Okay. So let me go ahead and take a brief pause there. Okay. So here, right, we have sine theta. Right, that's this one. We have a 5, I'll put the 5 out in front. Secant is really 1 over cosine, isn't it? Times tangent of theta d theta. Sine over cosine goes back to being tangent. Okay, with a 5. And now we have 5 integral tangent squared d theta. I could swear I've seen that somewhere before. Okay, so it doesn't matter how you do it. Like I said, your book tends to recommend this method. The way I was taught, they taught us this method instead of just trying to find the whole structure. But both of them work. Okay, and I will admit, sometimes seeing it this way is the harder of the two paths, and I default to doing this. So it's not like I always use one method or the other method. I just kind of mix and match. Okay. So what was tangent squared? Because I can't integrate tangent squared, right? If I do sine squared over cosine squared and I pick a u, I'm going to have like a mass in a denominator somewhere. We're going to have a du squared, which is, no, we don't do that. Okay, that's another one like up here. If you have it like this, du squared, like don't write that. You've made a terrible mistake. Don't do that. Okay. So what we're going to do with this tangent here is we're going to turn it back into secant squared minus 1. So we have 5 secant squared minus 1 d theta. And that's what we're going to integrate. Do you remember what the derivative of tangent was? The derivative of tangent was secant squared. It stands to reason that the integral of secant squared goes back to being tangent. All right, minus theta. Okay, by the way, that 5 goes to everybody, right? All right. Oh, don't forget your C. Otherwise, that's what you're going to get. All right. Tangent. What the heck is tangent? Going back to my triangle. Tangent is the square root of x squared minus 25 over 5. So this is 5. This is the square root x squared minus 25 over 5 minus. Well, theta is a little harder to get, okay? So what I'm going to do with theta, right? I mean, you could do this. Secant theta is equal to x over 5, and then say that theta is equal to secant inverse of x over 5. Nobody uses inverse secant. Nobody, okay? It's not even well defined. This is a terrible, I mean, it's not wrong, but it's a terrible idea. Tangent of theta, though, see how we have a tangent here? See, tangent of theta was equal to square root of x squared minus 25 over 5. Stands that theta is equal to the inverse tangent, right, of the square root x squared minus 25 all over 5. Okay, let's use that one. So we're going to have theta, we're going to have tangent inverse, so this is tangent inverse, right, that's my theta, times x squared minus 25 all over 5. Okay, see, and then we'll distribute our 5 through. So we have x squared minus 25 minus 5 tangent inverse of this. You can't put the 5 inside of this thing, right? It doesn't work that way. So tangent squared minus 25 over 5 here plus c. And again, the whole reason for doing that is because you have some kind of, right, some kind of parallelism here. Like music, when you do the same thing twice, they call it parallel. So we've got the same structure going on twice here, and this looks a little bit prettier than, you never want to open up a problem where somebody's like, oh, we're going to do secant inverse of, take that to your trig class and see what kind of a horror show you're going to get out of that. Like, people just don't like it. It's not even a good button on your calculator. This is inverse tangent's easy button on your calculator. It's not so nice. So that's kind of, what I'm looking for this stuff. When you are working your problem, because you kind of have to show your work, don't just magically pop here to here. If you want to make a shortcut, because there are shortcuts to this method, just saying, partial fraction decomposition, and to let me know, leave me a trail of breadcrumbs to follow you with. So, because if I just see like, here, and then poof, a miracle occurs. Like that's teachers get real suspicious when you do stuff like that. It's like, what happened between point A and point B? Where did that go? Where was that work? So if you want to use like let x equal -3, right, and then solve for something, or x equals +3, because you could do that right here, right? You could say let x equals 3. This b term tops out, and you just get 6a is equal to 2. A is equal to a third. You didn't have to go through all of this. Not that that was that painful. Not everybody gets the shortcut. That's okay. If you use it, this is a perfect opportunity. But let me know what's going on. Hey, using partial fractions, and then you can show a couple of few steps less. But you know, the whole point of this is to see, like, do you know what you're doing, and can you follow the techniques? Okay, same thing going on with this. Draw me the triangle. Don't just make the substitution like, hey, I just pulled this out of somewhere. Like, I just like, if your solution to doing this was to memorize it, you have a lot to memorize in your life, and this is not one of those things that I would carry around with me. Like, if you're going to be engineers, you're going to want to know, like, you're going to need like Young's modulus for commonly held materials. Okay, like there's other numbers and number of things that you're going to have to deal with, like this one. Right? Can never get that out of my head. Okay, so good luck with that. Again, I'm not trying to trick you. I'm trying to come up with problems that are going to be similar to these, not exact, but similar, so that you can, you know, have a reasonable final exam experience here. All right. Thank you.